So we're going to start with those other techniques, because you can imagine, as you'll see when you do that first lab, doing it numerically is tedious. You're going to have to plug in a lot, especially if you're a really big function. It's a lot of numbers you got to plug in. So there are some properties of limits that can help you, and then we're going to get into those algebraic. Graphically can always be used as kind of like a check. Algebraically is the big one, because a couple things without solving a limit, computing a limit algebraically, you got to remember all your rules of how to manipulate things algebraically. All right, so we'll get into some of those. First thing I want to go over are your limit laws. So this is actually another theorem, and it's all of the limit laws. And the limit laws are pretty straightforward. And it's the idea, the first one is a sum. So basically, and I'm going to put the first, all right, we'll just call it the sum. So the limit as x approaches a of two functions added together is equal to just the limit of each of those functions separately. That's all that is. So there are times it's actually easier to separate the functions to find the limits separately, and there are times it's easier to take two separate functions and put them together to find the limit. This law says you can do either one. And it is exactly the same for difference as well. And if you don't get all these written down while I'm going through them, it's okay. They're all listed very nice and neatly on one of your note slides. Okay? They're all there. All right? Be careful with subtraction, of course. Remember, subtraction order matters, where addition, it doesn't matter. All right? So just be careful with subtraction. The other thing is the constant. So if you have the limit of some constant times a function, you can pull that constant out front. That's all that says. It's a c times the limit. Okay. So if you got a big number, here's where this comes in handy. If we do something, I don't know, an application of business, we're dealing with really, really big numbers on the inside. When you go to plug a number in, you got to use those really big numbers. If you got something you can pull out and just multiply it once at the end, you can do that. That's all that does. It's just more of a convenience. So you've got that one. The product, you can separate products with limits as well. So the limit as x approaches a of f of x times g of x of two functions times each other can just be the limit times the limit so as you go through some of your homework problems, they just might present a limit in such a way where it would be easier if you apply one of these rules for you to solve it, okay? Quotient is good too, kind of same as product. And again, these are all in your notes, okay? So this is fine. You can separate and you can do just the limit of the numerator divided by just the limit of the denominator. I know, I didn't write the x minus x to a because it's... This is also forcing you to write limit note by copying these notes right now, because you know what happens when you take a test? You forget to put the x approaches on the test. Yeah, don't do that. She's like, no. Yeah, you know, so this is kind of forcing you to write the full notation out of g of x. Now, there's one caveat with this one. Anybody know what that is? What can't? As long as the limit of g of x does not equal what? Yeah. Yeah, you got to be careful there. So you just got to be careful with that. And then, of course, powers and roots. The limit as x goes to a of some function raised to a higher power, you can actually evaluate the limit first, get that answer, and then raise it to the power. Okay? In other words, you can do the limit as x approaches a, and then raise it to that power or to the root. When we talk about roots in this class, we use the fractional notation a lot, meaning the limit as x goes to a right? Isn't that how we write roots? We put 1 over. So the square root is written as something raised to the 1/2 power. And that's something, especially as we move into derivatives, you're going to start rewriting root symbols as fractions and taking things like 1/2 and just taking that function, or a square root of a function is a function to the 1/2 power. So you get used to writing roots that way. So some basic ideas, and these are theorems. There's a lot of little theorems. We're not going to go over all the little theorems, but some nice ideas are kind of what we already talked about, and we've already kind of mentioned this, and it's limits of polynomial and rational functions. And you've kind of seen it in some of the work we've done. And it's this idea. So let's assume P and Q are polynomials and A is some constant. So anytime you do a theorem, you write a theorem, you got to define what you're talking about. So we're going to assume P and Q are just polynomials. They are actually the standard letters, I don't remember, from Pre-Calc 1 to represent polynomials. P's and Q's are polynomials. And A is some constant. Okay, so for the first one, the limit as x approaches A of any polynomial function. You have already seen this. I've said this. These are the nice ones. All you have to do is take A and plug it into your polynomial. You're done. So it's just P of A. The You don't even have to do any algebra. It's just P of A. So if you assume P and Q are some polynomial and A is a constant, and you're taking the limit and it's clearly a polynomial, plug it in, you're done. For rationals, kind of works that way. So we know a rational function is one polynomial divided by a second polynomial, right? So it's fine. Your first step, by the way, in solving any limit algebraically is to go ahead and try to plug it in. Just take the limit you're approaching, plug it in, and see what happens. So your first step, of course, is, just calculate whatever P of A is over, that's a Q of A. But where do we run into a problem with rationals? This is all well and good as long as Q of A does not equal 0. And you'll know it, but you got to plug it in first to see it. So then it becomes, so what happens when it does equal 0, right? So let's take a look. Step 1, always try just plugging it in. Can I just plug in 1? Well, real quick, if you try to plug in 1, you get 1 squared minus 1 over 1 minus 1. No. Oh, this is where the fun begins. This is where the algebraic manipulation comes into play. And we got to figure out, what can I do with that limit algebraically that doesn't change its value, but I can play around with it. So look at that. X squared minus 1. What do you think the first thing you should attempt to do? What's your favorite F word from algebra? Factor. You got to factor. So can I plug it in? No. Now, factor. Okay, so one thing is to factor. So this is, again, be careful with notation. It is still a limit. What's x squared minus 1 factored? Oh, I was serious about the factoring part. I put that factoring. Yeah, if you got to go through that factor flow chart to remind yourself how to factor everything. Yeah, it's x minus 1, x plus 1, right? If you remember from pre-calc, this is actually what creates holes. What creates holes is when my rational function is in factored form, does something cancel? And in this case, does something cancel? Yes. And it's that thing that causes the issue. It's that hole that cancels away. Okay? That's what tells me there's a hole at 1, because it canceled. So now I have the limit. So watch, equals, it's still a limit problem. I didn't plug anything in yet. Now when I go to plug it in, I can stop using the word limit. You see that? What's the answer? Yeah. So again, not defined at 1, but you can still find the limit because you need to factor it first. So that's one major technique. You're going to have to factor when you see these. So you see a polynomial, you're good. You don't need to do anything. But the second you see a rational where you can't plug in your number. Now, don't start factoring everything. Sometimes if that wasn't an x minus 1 and that was an x minus 4, can I just plug in? Yes. If I wasn't approaching 1, but I wanted the limit as you approach 3, can I just plug it in? Yes, you don't need to factor. You only need to factor when you have that issue where it's going to disappear. Another algebraic manipulation, I'm just looking for an example because this is a biggie. So the algebraic manipulations can get tricky. I have one on here now. All right, here's one. You ready? Another example. Let's do the limit as x approaches 2. What did I say the first thing you always try is? Plug it in. Will it work if you plug it in? Try it. Go ahead. I can plug it in, right? Do you get an answer? What do you get? 3? Let's come to 3. Okay. Now if I had this. So the reason for me to do is I don't want you to see these crazy ones and think they're all going to be hard. Always, always, always just try plugging it in first. Let's try this one. Doesn't always have to be x. Can I plug it in? No, right away. You know, you start to do it and you went, oh, forget it. I can't plug it in. So does that mean I'm done? Call it undefined? Not necessarily. You got to be careful. So, and here's where limits get a little tricky. They're not so cut and dry. All right? It might be undefined. Problem is we don't know yet. It might be undefined. One of the things is this is one of the things you can multiply by, which may or may not work. Let's take a look. Is something called a conjugate. Again, may or may not work. You still might be undefined. But when you're dealing with limits, you got to try these algebraic manipulations before you can say it's undefined. So anybody remember what a conjugate is? I don't know if it's going to work. It's probably still going to be undefined. But let's try it. Conjugate, remember, is the radical plus 4. Remember that? All right, so when you multiply by a conjugate, do you remember how to multiply by a conjugate? What's cool about conjugates is middle terms. So this is just a binomial times a binomial. It's a crazy binomial, but it's a binomial times a binomial. But the middle terms are going to cancel. That's what's nice about conjugates. I only need to worry about multiplying this term times this term minus that term times that term. That's what makes it quick and easy. So let's multiply that conjugate out. Well, what's radical 16 plus h times radical 16 plus h? It's just going to be what? Yeah. Minus what? 16. Okay, leave the denominator as it is. We have an h times radical 16 plus h plus 4. All right, let's clean it up. This is algebraic manipulation. You're going to get really good at it. So we've learned one way of algebraic manipulation is factoring. Another way when you're dealing with radicals, which we didn't need in the first problem, but we're trying it in the second, is multiplying by conjugates. Watch what happens. What's 16 plus h minus 16? Everybody? Anybody see what's happening here? What can I do? I can cancel my h's. Remember, we're still going to 0. So what does my new manipulated limit looks like? It's the limit as x approaches 0 of 1. Can I evaluate it now? I'll move it up. Can I evaluate it? Well, we may not. We're going to plug in this number and see if we have to. Okay? What happens when I plug in 0 now for h? What's 16 plus, yes, question? Yeah. Yeah, 16 plus nothing. So it's basically 1 over square root of 16. I don't need to rationalize it because I can take the square root of 16 now. Does everybody see that? I can take the square root of 16, which is 1 over 4 plus 4. There it is. That's not undefined. The limit exists. But you would have thought you were done up here, right? And root does not exist and be like, okay, move on. No. So factoring, one method of manipulating your algebraic functions. Conjugates are another. At this point, I'm plugging in 0 with 16 plus 0. Yeah. I'm evaluating. So, and this is why you got to be careful with notation, because the second I start evaluating, there's no longer a limit word in front of there. Yes? I did what I should do in all of them first and just plug in what is the A value, which is our 2. When I plug in 2, oh, I get 3. It comes out to 3 if you do the math. Yeah. So, reason behind this. First one, just because you see radicals, don't jump to the conjugate. Try it first, right? We saw in number 1, we can evaluate it. Number 2, we saw real quick, we can't evaluate it because we end up with that 0 in the denominator. So what do we have to do? When you see radicals like this, a conjugate doesn't change the value of the problem, because ultimately, what did I multiply this by? What does this whole thing actually equal, everybody? I can multiply anything by 1. 1 is amazing in algebra because you can make a 1 look like anything you want it to look like, and we just did. And by doing that, we were able to evaluate that limit to 1/8. You can, if you're not sure, you can go to Desmos, you can plug that radical in, and you'll see where it's approaching 1/8 from both sides. Okay? This is where you're like, I gotta remember all that stuff from algebra. There's other things. we'll get some more examples because I want to get you to the lab today. We'll start the next class with a couple more algebra manipulations on Thursday and then we'll make a checklist for you of different algebra manipulations to try, okay? But I wanted to show you that now. All right, I'm going to pause this.